Hi everybody, I'm Ruben, and in this talk I'll be telling you about causality problems in digital advertising and how you can solve them using instrumental variables and PyMC3. So first, let's do a very short introduction about my company. Greenhouse is a digital marketing agency in the Netherlands, and 5 years ago we were acquired by WPP. WPP is one of the world's largest holdings of marketing companies. Within Greenhouse, we have always had quite a big technology department, and nowadays our marketing technology is used all over the world within the WPP network. Before we can dive into our problem, I quickly need to discuss some terminology. So first we have impression. Impression is when an ad is loaded once onto a web page browsed by a user. Then we have conversion. Conversions are the objective of a campaign. So it's a desired action of a user, for example, doing an online purchase or visiting a specific web page. And third, there's frequency cap. Frequency cap is a setting for campaigns which controls the maximum amount of ads a user can see of a specific ad. So now we have done the terminology, let's discuss the research question we want to answer. So advertisers can ask us, what is the optimal amount of impressions to maximize conversions? So this might sound like a very clear research question, but as we will see later on, it's not specific enough. So what do we do normally if we get such a research question? We start looking into our historical data. And here I'm showing you a couple of plots of what the historical data looks like. So what we're looking at is the probability of conversion of an individual user based on the amount of ads this user received, so the amount of impressions. And at first sight, these plots look amazing because they show very clear optima. However, if you think more critically, we actually can conclude that this cannot be true. One of the things that we see is that we see a clear optima and then quite a steep decline in the conversion probability. What this would mean is that after having the optimal amount of impressions, each additional impression would have quite a strong negative effect. Well, this sounds like something that makes sense because if you get a lot of ads, people might get annoyed and they will not be buying from your brand anymore. But being honest, what we see in the data here is much too extreme of a negative effect, so this simply cannot be true. And on the next slide, we'll be showing you why this is the case. But first, more importantly, if we look at the plot, the fourth plot down here, is that we get some pretty weird results. This plot will be suggesting that there is an optimum of maybe showing 40 or even 80 ads to each user. And of course, this cannot be a good thing. It can never be a good thing to have such a lot of repetitive ads of the same type of ad to each specific individual. So we should be more critical. So what's going on? Let's draw a causal graph. So we have a causality problem here, and the first part of our causality problem is a classical confounding problem. In this case, these confounders are unobserved. So, for example, these confounders can be how active is a user going to be on the internet anyways. So this kind of user activity both influences the amount of impressions we can show to a user and the probability that this user will have a conversion. However, this effect has nothing to do with the causal effect of impressions on conversion. Moreover, and this explains why we see such a negative effect in the plots that we've shown before, is that there's also a feedback loop from the probability of conversion towards impression. So why is this the case? What we do in these campaigns is once a user has converted, so visited a web page or purchased a product, this user is being excluded from the campaign. So what we instead see, instead of a negative effect, is that people that are interested in the products, they will have a conversion sooner, so they simply will never get to that amount of impressions. So yeah, this is not the same thing as having a causal negative effect of our impressions. So what can we do to solve these problems? Luckily, this is a perfect case for applying instrumental variables. But first, why do we need to use instrumental variables to start with? Because normally we would want to apply the golden standard, which is an A/B test, a random controlled trial, but in this case it doesn't work. The reason it doesn't work is because we cannot force users to exactly see a specific amount of impressions. However, what we can do is run an experiment, an A/B test, on the frequency cap. So we can make a random split across all the users, and without the user knowing it, have a different maximum amount of impressions a user can get. And actually, this makes a perfect instrument, which I will be showing you why this is the case on the next slide. So one important condition of the instrument, the frequency cap, is that the frequency cap itself is not influenced by our confounders, or we will still have a confounding problem. In this case, we know for sure this is true because we are running this A/B test experiment. So because we can control the random controlled assignment, we can be 100% sure that the frequency cap setting cannot be influenced by these unobserved confounders. Secondly, frequency cap as an effect on impressions, the amount of impressions users will get, and impressions will have an effect on the probability of conversion. However, there's no direct effect of frequency cap, our instrument, on the probability of conversion, our outcome. And this is also one of the conditions that needs to be satisfied to have a good instrument. So in general, it's quite hard to get a good instrument, so we can be very happy that we have a perfect setting for using instrumental variables here. So let's go back to the research question, because as mentioned before, we should be critical about what the advertiser is actually asking. So what is the optimal amount of impressions to maximize conversions? If the answer to this question would be something the advertiser implements as the frequency cap, so they're asking this because they want to know what the frequency cap should be, we actually do not need to use instrumental variables at all, because we simply would need to use the result of our A/B test. So the correct question would be, what would be the optimal frequency cap? In our specific case, we do care about the effect of impressions because we can use this in our bidding algorithms. So while we cannot set up an A/B test, we can change our bidding values based on the causal effects that we can use with estimating using instrumental variables. But more generally speaking, it's always a good thing to check before you start applying instrumental variable whether it's really the treatment of interest you're looking at. Because something you can A/B test is something you can influence, so maybe that's the treatment you were looking for after all. But in our specific case, it makes a perfect case because we do want to know the effect of impressions, not of frequency cap. Okay, so let's take a look at our data. So to be able to show you that our results are unbiased, we need to use simulated data. So let me explain you how this data is being generated. First, we have a maximum amount for frequency cap, which also indicates the maximum amount of impressions, which is both 7 in our example. Then there's the base conversion probability. So this conversion probability is related to the potential amount of impressions a user can get, which is unrelated to the causal effect. So this is the best way of thinking about it. This is the probability that's unrelated to the causal effects we're looking for. Then we have the effects. So these are the causal effects, and this is the exact values that we want to get unbiased estimates for. Then there are 2 more components to our data generating function. One is a distribution of these potential impressions. So these are not equally distributed, and as you can see, the higher the amount of potential impressions, the lower the probability we will find a specific user that is able to get this amount of impressions. So this will have an impact in our models later on. Then there's the distribution of the frequency caps, which is evenly distributed because we control this even distribution in our A/B test setup. And then we simulate this data for 1 million users. So let's take a look at our data. So what we can clearly see here is different buckets of frequency caps, which we used for our A/B test. And within each frequency cap bucket, we can see that there's a maximum to the amount of impressions users can get. Then we have the amount of users, the amount of conversions, and the non-conversions is simply the amount of users minus the conversions, which we'll be using later on. So we can group this data by impressions, in which we can see that for having fewer impressions, we have a lot of data, and we have less data for having a higher amount of impressions. And we can also group this data by frequency cap, in which we can see, because of our A/B test setup, that we have a more equal distribution amongst these groups. So let's have a look at this data if we plot it. This is simply calculating the probabilities, for which we do not use PyMC3 yet, but this gives our posterior plots. But for first, plotting the probability of conversion against impressions. And in this plot, we see a clear optimum and then a negative effect. And plotting frequency cap against the conversion probability. And this shows a very different shape, namely it's going up and the effect is getting less and less, but it's plateauing and it's actually never becoming negative. So this is an indication that something is going on. And now we will look into calculating the true effects of impression. So in this talk, we will take a two-stage approach. So in the first stage, we do an estimation of x using our instruments, which we'll use to get a fitted value of x, which can be used in the second stage. So only in the second stage, we will estimate the probability of conversion, not using the amount of impressions, but using the fitted values of the amount of impressions. So x hat in this case. So x hat is being estimated using the estimates coming from the first stage. And what's good to note here is that x hat itself is not deterministic, but actually as a beta A/B distribution, which we will come back to later on in this talk. So for estimating the x hats, it's actually really easy. We can just calculate the sample averages, so the average probability of getting a specific amount of impressions given a specific frequency cap. Here you can see what the data looks like. So as our rows, we have the different frequency caps, and in our columns, we have the first impression, second, third, fourth, fifth, sixth, seventh. And we can see the probabilities that a user who has had frequency cap 2 will have had the first impression, which is always 1 for all of our users, because we only have users that have at least 1 impression in our data set. And then there's a probability of 0.73 that a user with a frequency cap of 2 will also have had the second impression. So this is what our x hat data looks like. Okay, so let's look at our first model. What makes sense to start with is use a binomial regression in which we use the logistic link function to estimate our model. So this can be easily implemented to PyMC3, and we can already see in our posterior plots of beta that we get these different effects. However, if we plot this data against our true values, we can see that these numbers are not correct. So this is the case because we use the logistic link function. And to be able to do this kind of analysis, we actually do not want to have a non-linear relationship. So we need to change this to make sure that we have a linear relationship. So we will do this by switching to the normal distribution. And while this might feel a little bit counterintuitive, we can later on check whether we are okay with having this normal assumption, which we need to have to make sure that we have a linear relationship between our treatments, or x hat to be more specifically, and our probabilities. So in a normal distribution, our expectation is the probability times the amount of users, and for our standard deviation of our function, we simply calculate it using the average probabilities that we find in our data. So this is simply the variance of our binomial distribution, which we just typically calculate using our sample averages. Okay, so we quickly rewrite our model to include these components. And let's first check whether we are okay with our estimation by checking the probabilities that we get in our posterior distributions. So this is a plot of our posterior distributions, and what we can see is that for probabilities of all different amount of frequency caps, a density that is well between 0 and 1. So in this case, I do not need to worry that much about our assumption that we have a normal distribution, because our probabilities are nicely within our minimum and maximum, well defined between 0 and 1. So I think we're okay of making the assumption of our normal distribution. So because we now have a linear relationship, we can see that our two-stage method works. So in blue, we see the true values, and we can indeed see that for having a lower amount of impressions, we get quite nicely unbiased estimates. However, once we get to more and more impressions, the variance becomes bigger and bigger. So if you look at 6 and even 7, one of the things we see is that we even get negative effects. And actually, we're doubtful that these negative effects in reality. So yeah, this is not something that we can practically apply into our bidding algorithms. So what do we do? So we will start making assumptions. This is the core of modeling. It's thinking about your variance and bias trade-off. So we want to reduce our variance in our estimates of our effects for having a higher amount of impressions. But as we will see later on, we will introduce a little bit of bias by doing so. But first, let's start with a very simple assumption. It's the assumption that our effects are at least 0 or larger. So we have only positive effects. So I can show you that using Bayesian statistics in PyMC3 is really easy to include this. So what we simply do, instead of having a normal distribution for effects, we switch to half normal. And we do need to make a quick change in adding our constant term in this case. So this is how we do our implementation in PyMC3. And this is what the results look like. Well, we are still not too happy with these results, because we can clearly see that we only have positive values in our posterior distributions, but also we see a lot of bias, and especially with having a higher amount of impressions. So just assuming that the effects are positive is probably not the right thing to do. So back to making assumptions. So what do we want to do instead? We want to make assumptions about a parametric form of beta. So what functional form might beta have based on the amount of impressions that the user gets. So, and this is our approach. So instead of estimating individual effect for each amount of impressions, we choose a functional form, which is taking alpha 0 plus I times alpha 1, and take the exponent of those. Yeah, so this is the way we will be working. So instead of having to do an estimate for every different amount of impressions, we basically just have two parameters, alpha 0 and alpha 1, which will together give the effects of every different amount of impressions using this functional form. So again, this is what our model looks like. And we can see a very, very clear difference here. So we see that the variance has become much, much less. Also, what I included here is the effect for the first impression. So you can see that it's a little bit off. And actually it was impossible to have an estimate of the effect of the first impression simply because we cannot compare against people who haven't had any impression because those weren't in the data, but because we made an assumption, we can have some kind of estimation here. But more specifically, if we look from having 2 or more impressions, we can see the variance is much, much less. We get quite nice biased results for the lower impressions. However, what we like a little bit less is if we get up to 7 impressions, we can see that there is some bias being introduced into the model. So here we zoom in a little bit more specifically. So ideally, we do not want to have the true value so close to the 3% percentile in our plot. So maybe our assumption about this parametric form is a little bit too strict. So what can we do to soften this assumption? We can include hierarchy into our model. So by including hierarchy, we allow the model to take the functional form as a starting point, but be a little bit more flexible about also having individual effects inside. So basically the thing we changed is instead of having one single alpha 0 I, is we have again individual level alpha estimates. However, they are all linked together with our alpha 0 in our hierarchy. So this is our implementation in PyMC 3. And now let's take a look at what our plot looks like. So actually what we're looking at now is something that looks quite good. We still see very powerful low variance estimates for having 2 or 3 impressions. But once we start coming to having a higher level of impressions, the data becomes less, and you see not such extreme variance as we have seen in our first estimation, but the model is still having some flexibility, or as a little bit softened the assumption about the parametric form we had before. So we can nicely balance between these two by including the hierarchy. So this is something that we would really like to implement, because the variance is not too extreme, but also we're not overconfident in the data and unnecessarily introducing bias into our model. However, there's one more thing to discuss. Our posteriors are a little bit too optimistic about variance. So what we did so far is we assume x hat to be deterministic, while in fact it's also an estimation, including estimation error from our first stage estimation. So in this specific case, we know the distribution of x hat because it's as a beta distribution. So as a result, the estimation error with our estimates is in fact larger because of estimation error in this first stage. So the question now is, how can we account for this estimation error in the first stage? So there are a few things I tried that didn't work for me. So one of the things I was thinking about, because we know this conjugate prior distribution of x hat, we can try to use a Tiana random stream to do this random sampling inside our MC estimation. So unfortunately, this didn't work for me because I had quite some troubles in change breaking down when I tried to implement it in this way. Also, an alternative is actually not using this beta distribution, but do an estimation of x hat inside the same PyMC3 model, which basically means estimating both stages at once. So also this didn't really work for me. MC was very slow, and I didn't really achieve convergence of this model. So what did work for me thinking about this is doing some kind of a bootstrapping approach. So basically what we can do is we, instead of estimate our model once, we can do a random draw of our x hat from our beta distribution and estimate our model n amount of times. And because we have these posterior samples, what we can simply do is take maybe only 100 samples from our distribution every time we estimate our model, and simply use all those samples for different iterations and take them together to get a new posterior distribution that does include this estimation error inside our x hat. So this is what the code looks like. So in this case, we take 100 amount of runs, and each time we do a random draw from our beta distribution to create a x tilde, which we will use for estimation instead of our x hat. So this will be randomly sampling, and in each iteration we take 100 samples and we use this to come up with new posterior distribution. So this is what the result looks like, and as you can see, there's really a lot of little difference in variance. So it doesn't really look like the variance increased a lot. Still, I've been checking the method and it seems to be working. But what I do think the reason is for the variance not being increased that much is because the variance in the first stage estimation is extremely small in comparison to the variance we get in our second stage estimation. So as said, why does this seem to have little effect? So the variance in x hat is small in comparison to the variance in the conversion probability. So, and I think it will be a very interesting thing to discuss during our Q&A is what your approach will be for incorporating the variance of the first stage into the estimation. So let's do a little bit of a recap. When can we use instrumental variables? When you need to have unbiased estimates of causal effects. You cannot A/B test a treatment of interest, but you can run an A/B test on something that influences the treatment of interest, but not the outcome directly. Also, you're sure you don't just need the results of the A/B test, because it might be what you can A/B test is in fact the treatment you're looking for after all. So to come to a conclusion, instrumental variables can be applied to quite specific setups. However, you can get guaranteed unbiased estimates for causal effects for something you can't A/B test. In this talk, I showed you how to estimate this using PyMC3 following the two-stage approach. And when you run into problems with variance, you can start modeling by making parametric assumptions, which I also showed you how to include them into your PyMC3 model. Then hierarchical modeling can be used to soften these assumptions. And in this talk, I showed my version of solving the problem of including the estimation error of the first stage with my bootstrapping method. And I'm very much looking forward to hearing your thoughts on what will be the best way of including this estimation error into our estimates. Well, thanks for your attention, and I'm very much looking forward to having your questions in the Q&A.